Hello, this is Gregory Maxwell, and this lesson is going to be on functions. And I'd like to give credit to Professor Shauna Hayter for a number of the slides that will be used in this presentation. She created them, and I'm giving her the credit for these slides. Function. Let's start off with the definition of a function. We'll start off with a relation. A relation is a set of ordered pairs. Basically, a relation is a link between output from inputs and outputs. The input values are called the domain values, and the output values are called the range values. So, for example, we have a set of ordered pairs here, and it's a set with points 2, comma 3, -1, comma 5, 4, -2, 9, 9, and 0, -6. The input values are the values listed first, and those are the x values, which would be then 2, -1, 4, 9, and 0. And if we usually put the domain in numerical order. The range are the output values, the values that are the input values are the link to the output values. So the range values would be the values that we will receive. We start with the domain and we end with the range. So the range values here are 3, 5, -2, 9, and -6, which we put in order here from least to greatest. I'm sorry, it should say least, not smallest. So let us continue here. And let me just quickly make a quick adjustment. This should not be smallest. This should be least to greatest. Least to greatest. Now, let's take another look at a way to represent functions here. This is called a mapping diagram. It tells you how the numbers are linked from the domain to the range using arrows. So for example, in this relation, we are going to link the number 1 to 6, number 2 to 2, 3 to 4, 4 to 8, and 5 to 10. So the ordered pairs that correspond with this relationship are 1, 6, 2, 2, 3, 4, 4, 8, and 5, 10. Those that would make it the relation. Now, in this case, this relation happens to be a function, and let's see why that is the case. So let's say we start out with two non-empty sets. Non-empty means each set has an item in it, has an element in it. A function, this is the formal definition of a function. A function, let's call it f, from set x into set y means f takes things from x and links them to things in set y. We start at x and we enter into set y. Is a rule of correspondence, also known as a relation. That means a way to link the two numbers, the two sets, that associates with each element x in the set x. That means each of the elements in set x, exactly one element y in set y. That means each element in set x links up with only one element in set y. Now that's a mouthful. So let me just illustrate and I'll give a couple of comments about that. First of all, a function has three parts. It has a beginning point, the domain, an ending point, the range, and a way to get from the beginning to the end in such a way that each number in the beginning set, the domain, has to be used, but each number can only be used one time. Kind of think of it like taking a trip. Let's say that you're trying to travel from city A to city B. The transportation system is a bus, and the people on the bus all start in city A, but they don't all start at the same location. So the bus picks them up at different spots, and then the bus drops them off at city B. Sometimes the bus may drop off multiple people at the same spot. Sometimes the bus may drop off some persons one place and another person another place, but everyone that got on the bus in city A gets off the bus in city B. Now, the function here is the whole system. You have a starting area, city A, the way and an ending area, city B, and the way to get from city A to city B, which is the bus. It's important to note that everyone that gets on the bus in city A has to get off the bus in city B somewhere. Now, it doesn't mean that they everywhere in city B, that doesn't mean that we everyone everywhere in city B has someone that gets off there, but everyone that got on in city A must get off somewhere. And one person cannot get on the bus in city A and get off the bus at two different locations in city B. Although two people can get on the bus at two different locations in city A, but get off the bus at the same place in city B. So what we're saying here is everyone has to get on the bus, but they can only get off the bus at one place at a time. They cannot get off the bus. Um, One person cannot get on the bus one place and get off the bus at two different locations. So the domain must all be used, but each value must be used once. So here's an example here. In this relation, 1 goes to 4, 2 goes to 2, 3 goes to 10, 4 goes to 8, and 5 goes to 6. Let us see. Did we use each x value, each domain value? Yes, we did. All x values are assigned. Good. Did we use all the y values? Yes, but that doesn't matter. What matters is we use all the x values, and each x value is only used one time. So each x value only corresponds to one y value. Is that the case? Yes. So that makes this a function. It satisfies all the conditions for a function. So we're gonna look at another example in a minute. What about this one here? 1 goes to 2, 4, 2 goes to 4, 3 goes to 4, 4 goes to 4, and 5 goes to 4. Is this a function? Now, if we stop and think about it, for it to be a function, we need two conditions here. We need all the domain values to be used, and each value should be used once. Are all the domain values used? Yes. Every value goes to something. Is each value used once? Yes. Each value is only used once. This is like my analogy with the bus again. Each person may have gotten on the bus at different places in city A, but they all got off the bus at the same place in city B. That's fine. That allows us, this is still allowed as a function. Each value must only go to one value, but the one value can come from everything. Now let's take a look at another example here. A good example that you can relate um, is to which you can relate is that you can link students in a college algebra class in a semester. Those students are the domain values, and their grades are the y values. Each student must be assigned a grade and can only be assigned one grade, but more than one student can get the same letter grade. For example, let's say student 1 gets an A, student 2 gets an E, student 3 gets a D, student 4 gets a C, and student 5 gets a B. In that case, we're talking about a function because each student gets one grade and every student has to get a grade. But what if student A got both a B and an E? That doesn't make sense. That doesn't work. So this would not be a function. The reason? One input cannot have more than one output. One student cannot get two different letter grades at the end of the semester. Okay? So this situation is not a function situation because one input has more than one corresponding output. Let's try this one here. In this case, all students except student number 3 gets a letter grade. So is this a function? Answer is we didn't use all the x values, and since we did not use all the x values, then this is not a function. It is a relation, but it is not a function. In a function, all the domain values need to be used. And let's take a look at this one. Each student gets a letter grade. Student numbers 2 and 3 got the same letter grade A, and no one got a D. Is that allowed? Yes, as long as all the x values are used and each x value is used exactly one time, no more, no less. Then we're talking about a function. Now let's talk a little bit about function notation. Notation just means how do you write something to represent something meaningful. Now, the notation for function is the name of the function. In this case, the name of the function is f, and it tells you what variable represents the input values, in this case, x. And this is read f of x. That means the function f acts on the the main value x, and then over here on the other side it tells what f does to x to give an output. So we read this: f of x is equal to 2x squared minus 3x plus 6, and it means whatever value I choose for x, the input value, I will do this operation to it: 2 times x squared minus 3 times x plus 6 to get the corresponding output value. So we call that function um, this is the function notation. And please note that this is not a multiplication. This is not f times x. This is f of x. In other words, it means f operates on the variable x. All right, f f is the function, and it does something to x, and what it does is this operation right here. Now let's take a quick example. Our function that we just used as the example is f of x equals to 2x squared minus 3x plus 6. Let's find um, f of 2. F of 2 means if the input is 2, we're going to replace all the x's with 2. And so we get 2 times 2 squared minus 3 times 2 plus 6. And then, of course, we'll use PEMDAS. We'll work on the exponents first, and then we'll do the multiplications. So 2 squared is 4, then 2 times 4 is 8, negative 3 times 6 is negative 6, and then the 6 is added on, and then we do the addition and subtraction. So the output is 8. So what we're saying here is that when the input is 2, the output is 8. And what we tend to do is we'll say that there's a corresponding ordered pair that goes with that. The corresponding point would be input is 2 and output is 8. Let's take a look at another example. What if instead of 2 we insert negative 2? We go about the same way. We replace all our x's with negative 2, and then we do PEMDAS. Negative 2 squared is 4, so 2 times 4 is 8. And then negative 3 times negative 2 is positive 6, and then plus 6. So the output now is not what we got before, not 8 as before. The output in this case is 20. So the corresponding ordered pair then would be the corresponding point would be input of negative 2 and output of 20. Let's continue. Let's say we want to find f of k. Now, k is just a number that we're going to substitute for x. What that means is wherever we see x, we will replace that x with k. Well, all that does is switch out the variables. So instead of saying 2x squared minus 3x plus 6, we end up with 2k squared minus 3k plus 6. No difference really in the structure. All we have is an interchange of the variables. Now, what if instead of replacing it with k, we replace it with 2k? Same thing. We replace all our x's with a 2k in parentheses. So wherever I see x, I will replace it with 2k. Then I will use the rules of exponents and multiplication and addition, PEMDAS rules, to simplify. 2k squared means 2k times 2k, so that is 4k squared. And then I'll multiply 2 times 4k squared, that gives me 8k squared. Negative 3 times 2k is negative 6k, and then plus 6. We cannot simplify this anymore because these are not like terms, so we cannot add them together. So the answer then is if the input is 2k, the output is 8k squared minus 6k plus 6. Let's try another example here. What if we had g of x is equal to x squared minus 2x, and I want to find g of 1 plus g of negative 4? All this means is that we're going to evaluate the function when x is equal to 1. That means when the input is 1, what's the output? And when the input is negative 4, we evaluate that as well. And when input is negative 4, what's the output? And then we'll just add the results. So g of 1 means replace all the x's with 1. So we get 1 squared minus 2 times 1, which is 1 minus 2, which is negative 1. And g of negative 4 is the square of negative 4 minus 2 times negative 4. That's 16 plus 8 is 24. And then we're going to add those two values. So we're going to add negative 1 plus negative plus 24, and that gives us 23. And that's how simple that is. Now, before we move on, we just have to look at one more concept, and then we'll do some examples. The idea of the domain of a function. The domain are the values of the variable that are allowed to be plugged in so that we get a corresponding output. Now, a function has what we call a natural domain, which means all possible, in this case, real numbers, that when you insert those into the function, you get an actual real number answer. Now, when you're trying to find the domain of a function, just remember it's the values of x that when you plug them in, you get an answer. To find the natural domain, that means all the possible values that can work, we have to remember some rules of mathematics, rules of real numbers. Namely, you cannot divide by zero. When you divide by zero, you get no solution. That is an undefined term in mathematics. It does not give an answer. Also, if you find the square root or any even root of of a of a negative number, you do not get a real number answer. So if you want a real valid function, that means a function whose answers are real numbers, whose outputs are real numbers. If you're taking a square root or an even root, your input under the radical, the radicand, as it's called, cannot be negative. It has to be a positive number or zero. So if under the radical works out to be a negative, or if the denominator works out to be zero, then we have to call those illegal values. We have to throw them out of the domain, and then we can use all the other possible values. So we call those domain restrictions. And there is another type of domain restriction, which we'll do later in the course, called inputs of logarithms. Now, generally speaking, if there is no domain restriction, then all real numbers will work for the natural domain. For example, in this function f of x equal to 2x minus 1, this has no domain restrictions. Since we're not dividing by a variable, and since we're not doing a square root or any even root of a variable, then we have no restrictions. So the domain is all real numbers, or in interval notation, negative infinity to infinity. In this case, however, we have a rational expression where a rational function where the denominator has a variable x minus 2. There is a place where x minus 2 may work out to be 0, namely if x is equal to 2. So what we have to do then is say, hey, we can use any value of x except when x is equal to 2. Please note that there's nothing wrong if the numerator works out to be 0, because 0 divided by any other number is 0, but the denominator is not allowed to be 0. So we cannot use the the value of x equal to 2. Any other value will work, but we cannot use 2 as an input. So our restricted domain is that x cannot be 2. So this is the set of all x values such that, that means with the following condition, x is not 2. And in interval notation, we can write it like this. Anything to the left of of 2, sorry, with the parenthesis, union anything to the right of 2. That is the interval notation. Let's go on to the next example. What is the domain of h of x equal to square root of x minus 4? In this case, we have a variable under a radical, and it's a square root. So there is a restriction here possible. Under the radical only works, the function only gets a real number answer if under the radical is non-negative, namely greater than or equal to 0. So we take there under the radical and we set it greater than or equal to 0, then we solve for x. And we realize that that only happens if x is greater than or equal to 4. So therefore, the domain of this function is the set of all x is, all real number x is, such that x is greater than or equal to 4, or the interval notation is bracket 4 to infinity. All right, now let us quickly take a quick recap then of what we just said about domain restrictions. What we want to do to find the domain of a function is find all the values of x that do not work. Find all the values of x that do not work and throw them out, and then use everything else. And those values of x are values that cause the denominator to equal to 0, or the values of x that are negative. So if you want to find when it's under a square root or an even root. So if you have a situation where there's a variable in the denominator, find out whatever causes the denominator to be 0 and throw that out. And whenever you have a square root or an even root, only use those values that are non-negative, greater than or equal to 0. So let us try an example here. Let's try an example here. We have a function here, and we want to find these values. F of x equal to negative 2x squared plus x minus 1. We want to find f of 0, f of negative 1, f of negative x, negative f of x, f of 2x, f of x plus 1, and f of x plus h. Let's start with f of 0. So for part A, f of 0 simply means replace all your x's in the function with 0. So it's negative 2 times 0 squared plus 0 minus 1. Now negative 2 times 0, 0 squared is 0, and negative 2 times 0 is 0, and 0 plus 0 plus negative 1 is just negative 1. So the answer is negative 1. So part B, if I replace x with f of negative 1, means we replace all your x's with negative 1, and I'll put that negative 1 in parentheses, and then proceed. If I continue with that one, I will get negative 2 times the square of negative 1, which is 1. And then when you add a negative 1, you're just subtracting 1. Basically, then we have negative 2 minus 1 minus 1. That will give you a negative 4. So f of negative 1 is negative 4. Now let's try something a little bit more tricky. We're going to do f of negative x. And all that means we're going to do is we're going to replace all our x's with negative x instead. And I'm going to put that in parentheses. Now, when I square a negative, I get the same value as when I square a positive. So the square of negative x is just the same as x squared. And when I add a negative, I just get, it's the same as subtracting the corresponding positive. And that's all we get. This is all we can do. We cannot simplify this anymore. We cannot combine like terms. So we're done with this question. F of negative x is negative 2x squared minus x minus 1, which is different from what we had, because in the original, it was a positive x, not a negative. Then let's go on to part D. We have negative f of x, negative f of x. Negative f of x means just take the whole f of x function and make it negative. So I'm going to put the f of x function in parentheses, negative 2x squared plus x minus 1, and I'm going to put a negative in front, which means change all the signs and basically multiplying each term by a negative 1. So that gives me a positive 2x squared minus x and plus 1. So a negative f of x is 2x squared minus x plus 1. Now let's go on to part F. Part F looks a little bit more challenging than even the ones we had before. It's f of x plus 1. And to do that, we're going to replace all our x's with x plus 1. So we get negative 2 times quantity x plus 1 squared plus x plus 1 and then minus 1. We're going to use PEMDAS here. We're going to distribute this square, but that's a plus, so we really have to just multiply that x plus 1 by itself. And this plus x plus 1 doesn't change anything because you just have an addition. So we can continue here. So when I distribute, I get negative 2 times x squared plus 2x plus 1. And then I have my plus x here because it just turns out that this 1 and this negative 1 undo each other. So I continue here. I distribute my negative 2. I get negative 2x squared minus 4x minus 2 plus x. So my final result then, f of x plus 1 is negative 2x squared minus 3x minus 2. And that, of course, is because we combine this negative 4x plus this positive x. And that is the answer, systematically. Remember your exponent rules when you're doing these, because those matter. Let's do this last one here in this example, E. We want to do f of x plus h. And again, just as before, we're going to replace all our x's with x plus h in parentheses. And then we perform the operation. Negative 2 times x plus h squared is negative 2 times x plus h times x plus h. And then this x plus h doesn't need anything because it's a positive 1 in front of the parentheses. And we have a minus 1 here. So let's continue here. And we continue, we get negative 2 times x squared plus 2hx plus h squared. That's what you get when you multiply these two. And then we're going to distribute that negative 2, and we end up with negative 2x squared minus 4hx minus 2h squared plus x plus h minus 1. And unfortunately, there are no like terms, so this is all we can do. This is what we end up with. That is our answer, and that's that. Now let's go on to the next example here. F of x now is equal to x over x squared plus 1. So let's go and continue. Part A, f of 0 is equal to 0 over 0 squared plus 1. Well, that's just 0 over 1, which is 0. So f of 0 is 0. Then part B was f of negative 1. F of negative 1 means negative 1 over square of negative 1 plus 1. That's just negative 1 over 2, or just negative half. Then let's go for f of negative x. It's part C. F of negative x means replace all your x's with negative x. So we have negative x on top, the square of negative x at the bottom, plus 1. Now, that turns out to just be negative x on top, and then the square of negative x is just x squared. Because when you square a positive, you get the same as the negative as what it gets when you square a negative. So that's it. Negative x over x squared plus 1. So we're done with that question. We'll go on to part D. What about negative f of x? All that means is I'm going to take my function and multiply by negative 1. Negative 1 times x over x squared plus 1. The thing is, when you multiply by a number, you only multiply the numerator when you multiply it by a whole number. So I'm only going to multiply that negative 1 to the numerator. So that gives me negative x on top. And the denominator is just x squared plus 1. And so as you see, in this case, f of negative x happens to be the same as negative f of x. When functions like that, when things like that happen with functions, they have a special name. That special name is called an odd function. But we'll deal with that in another lesson. So we have now f of 2x. And again, all we do is replace all my x's with 2x in the original function. So it's 2x over the square of 2x plus 1. And the 2x on top just stays the same. We square the 2x at the bottom, we get 4x squared, and then plus 1. And that's all we can do. And that's the end of that part. Now let's go to part F. F of x plus 1. F of x plus 1. And that is, replace all the x's with x plus 1. So it's x plus 1 over the square of x plus 1 plus 1. And that will just give me x plus 1 on top over, when you square x plus 1, you get you get x squared plus 2x plus 1. And then, of course, you get another plus 1 here. So in other words, I'm saying this little piece here works out to be that there. And when you combine like terms, you end up with x plus 1 in the numerator and x squared plus 2x plus 2 in the denominator. And that's the end of that part. Let's go on to part H. Part H. part H, we are going to do F, sorry, not part H, sorry, part E. Oh, I just realized that I made an error in my notation here. That's supposed to be a G. G comes after E. That's not a problem. It's just when we're doing the parts. So part G is F of X plus H. All I do is replace all my X's with X plus H. So where I see X, I'll put X plus H. And in this case, in the denominator, I'll put X plus H in parentheses. When I square X plus H, I get X squared plus 2HX plus H squared. And then of course I'm just going to add the 1. And since there's no like terms, we just leave it like that. So that would be the answer to that expression right there. Let's go on to another example. This time f of x is equal to x squared, a square root of x squared plus x. So for part A, f of 0 is equal to the square root of 0 squared plus 0, and that's just 0. And let me just pause here and just remind you that when you're watching this video, I encourage you to try these questions on your own first and then check to see if you got a similar answer that I got. Let's continue here. F of negative 1 is square root of negative 1 squared plus negative 1. That's just 1 minus 1, which is 0. So it's the square root of 0, which is 0. So f of negative 1 is also 0. Let's go with part C. F of negative x is equal to square root of the square of negative x plus negative x. And when you square a number, you get the same as when you square negative, you get the same as when you square positive. So the square of negative x is the same as x squared, and plus negative x is just minus x, and that's all we can do with that. Let's go on to f of 2x, part D. F of 2x. So f of 2x is equal to square root of the square of 2x plus 2x. When you square 2x, you get 4x squared. So this becomes the square root of 4x squared plus 2x. And we can leave it like that. Let's go on to the next example, the next part, part F. F of x plus 1. Again, we simply replace all our x's with x plus 1. And then simplify. When you square x plus 1, you get x squared plus 2x plus 1. And then, of course, we're adding the x plus 1. We simplify that. We get square root of x squared plus 3x plus 2. So that gives us the answer for f of x plus 1. Let's go on to the last part of this example, which is part G, f of x plus h. And again, we are going to just replace all our x's with x plus h squared plus x plus h. So when you square x plus h, you end up with x squared plus 2hx plus h squared, and then we have plus another x and plus an h, and that's all we can do. We cannot simplify that anymore. So we see a number of examples here where we have values of functions being found, and we just evaluate the functions by replacing all the x's with their corresponding requested input. Now let's do this question here. It says find the domain of this function. Now again, to find the domain, we have to look for domain restrictions. If there are no domain restrictions, then we indicate that since there are no domain restrictions, then the domain is all real numbers. And if there are domain restrictions, we make adjustments accordingly. In this case, we have no variable in the denominator since um, we do not, since no variable since we have no variable in a denominator and there's no variable in under a radical, then what we have here, we have no domain restriction. And if we have no domain restriction, then the domain then is all real numbers. So the domain is therefore negative infinity to positive infinity, all real numbers. In this case, for the next example, we do have a variable in the denominator. So our possible domain restriction occurs if x squared plus 1 is equal to 0. So our possible restriction is if x squared plus 1 is equal to 0. Well, that would require that x squared is equal to a negative 1. And since when you square a real number, you don't get a negative, this would not be a real number. So this is not. So that would require that x is equal to positive or negative the square root of negative 1, which is plus or minus I. That is not a real number. And our domain is only for real numbers, so not a real number. And since there's no real numbers restrictions, so no restrictions, no real number restrictions, which is the only ones we're looking for. We're looking for functions that have inputs as real numbers and outputs as real numbers. So we have no real number restrictions, so therefore the domain is again all real numbers, because there's no real number value that would make this denominator equal to 0, and there are no other indicated restrictions. Again, we have another possible domain restriction here. So let's take a look at what this one will give us. So for this domain restriction, we would have to say the denominator x cubed minus 4x would be equal to 0. Now that's a polynomial, so we're going to have to factor that. We can factor it, we get x times x squared minus 4, which factors to be x times x minus 2 times x plus 2. So we're talking about x times x minus 2 times x plus 2 equal to 0. And as you can see from that polynomial, that implies that x could either be 0, x could be negative 2, or x could be positive 2. And we don't want any of those. If I plug in 0 into the denominator, I get 0. And that's not allowed. If I plug in negative 2, I get negative 8 minus negative 8, cause negative 8. Negative 2 cubed is negative 8. And negative 4 times negative 8 is positive. Negative 2 is positive 8, so that would be 0. And then this other case would be 8 minus 8. So we don't want x to be any of those. Those are my domain restrictions. So the domain then is the set of all x's that are real numbers, of course, such that x is not negative 2, 0, or 2. In interval notation, we can write that as negative infinity to negative 2 union negative 2 to 0 union 0 to 2 union 2 to infinity. And that is a little closed up here, but that is the interval notation. A little tedious. It's saying is use everything except for negative 2, except for 0, and except for 2. Now let's continue. Part D. F of x equal to 4 over the square root of x minus 9. In this case, we have a domain restriction. We are saying that the x minus 9 has to be greater than or equal to 0. However, we also need it not to be 0, because if it's equal to 0, we'll be divided by 0. So we can only say x minus 9 is greater than 0. I'm going to move this down a little bit to create a little bit of space. So we're saying that x minus 9 cannot be 0, and x minus 9 has to be greater than or equal to 0, which means overall that x minus 9 has to just strictly be greater than 0. So that means x has to be greater than 9. So as long as x is greater than 9, this will work. If it's less than 9 or if it's equal to 9, this won't work. If x is equal to 9, we'll have 9 minus 9 in the denominator. The square root of 0 is 0, but we can't divide by 0. If we have a negative, if we have a number less than 9, we'll get a negative under the radical. That doesn't work. But if we have a number greater than 9, we are fine. So the domain here is parentheses 9 to infinity, because we're saying numbers to the right of 9. Now let's try this little challenging one here. We'll go into more details with these up later on. In this case, we're saying we need the domain restrictions. We need t minus 4 to be greater than or equal to 0. And also at the same time, we need 3t minus 21 to not be 0. Because the numerator on the radical has to be non-negative, and on the denominator cannot be 0. Well, in this case, we just solve for t to get t is greater than or equal to 4. And at the same time, when we solve for t here, we get 3t can't be 21, so t cannot be 7. So if we put those two regions together on the number line, let's see what that would look like. We're talking about, for this one, we're talking about all numbers to the right of 4, including 4. So we're looking at from 4 to the right. And for this, we're looking at all numbers except for 7. So we're looking at numbers to the left of 7, and we're looking at numbers to the right of 7. And since this says and, we're looking for where those two regions overlap. So they start overlapping at 4, they stop just before 7, and start overlapping right after 7 again. So then the domain of this function is basically the set of all x's such that x is some number between 4 and 7, or x is greater than 7. And I put my interval notation version, which is what version I prefer you to write it, is from bracket 4 to 7, union 7 to infinity. So that is the domain restriction for the function. So as you can see here, this is the domain of the function. So as you can see here, there's a lot to consider when you talk about functions. Remember, a function has 3 parts: an input, an output, and a way to get from one to the other. Now let's talk a little bit in the last portion of this lesson about graphs of functions. Let's talk about graphs of functions. So we already graphed equations. Well, you've probably seen that before, graphed equations with straight lines and so on. Now, functions are graphed in a similar way. You basically identify inputs and then find the corresponding output. Now, if this is a straight line, it's relatively easy. You just need one point and the slope to get to another point. If the equation is in slope-intercept form, then it's perfect for a function. So f of x equal to 3x minus 1 is a straight line function whose slope is 3 and whose y-intercept is -1. So we start at -1 and use the slope to go up 3 units and over to the right 1 unit, and that gives me another point, and then I can just join those 2 points. And what I have here is the graph of a straight line. That is the graph of my function right there. Now, That said, and this is useful in other areas as well, when we're talking about functions, we have the input variable, which is the variable that we choose. The person who's doing evaluating the function chooses the input variable, so it's called an independent variable. But the output variable depends on what is chosen and what function you plug it into, so that's called the dependent variable. So independent variable is a variable that is inputted, and it depends on it's an independent choice by the person evaluating the function, and the dependent variable is dependent on what function you have and what you plug in. Next, we have what we call the vertical line test. The vertical line test is just using the definition of a function in a graphical note situation. It says when you draw the graph of a function, each x value should only have a corresponding y value. That means if you draw a vertical line through any x coordinate, it should only cross the graph of the function once. Here's a classic example. I have a graph of a function here, and I'm drawing a series of vertical lines, and each vertical line only crosses the function at one point. If that happens, if the function is only crossed at one point, no more, maybe less, maybe not at all, but it cannot be crossed more than once, then we have a function. On the other hand, if I have a graph where when I draw a vertical line somewhere, it crosses it more than once, anywhere at all, once there's a place where the graph crosses the straight line, vertical line, sorry, crosses the graph at more than one spot, then that is not a function. Here's another example. If I draw a vertical line here, it crosses once. Here, crosses once. Here, crosses once. Here, crosses once. What we have here is a function. Wherever I draw a vertical line, we have ourselves a function. We have ourselves one intercept on, sorry. So that is not a function. That is a function. Now let's take a look at these two examples here, the graph of y equal x squared and the graph of x equal to y squared. If I draw a vertical line anywhere on the graph of y equal x squared, we end up with only one intercept. So that means we have ourselves a function. What if we draw a line here for the one graph? It only touches it once. That's fine. But if we draw another line, it touches it more than once. So that is not a function. The graph of x equal to y squared is not a function. So let's go on to analyze a little bit about what the graph of a function looks like. So is the graph a function? Yes. Wherever I draw a vertical line, anywhere on this graph, it would only cut it once. So that's a function. What is f of 0? To find f of 0, what we do is look for 0 on the x-axis and then draw a vertical line there to see where that vertical line crosses the graph. And that point, the y-coordinate is the value. So f of 0 is 2 because the y value for where that x graph crosses, that the y value that corresponds to 0 on the x-axis, the y value in the graph is 2. What is the domain of the function? Since the function continues forever to the left and forever to the right, and there's no breaks in between, then the domain is all real numbers. What is the range? Since the graph goes downward forever and goes upward forever, and there's no break in between, the range is also all real numbers. That means this function has no domain restriction and it has no limitation on the y values as well. This function is unbounded. So the range and the domain are both all real numbers. What about this graph here? Is it a function? If we draw a vertical line anywhere, the vertical line will touch the graph at most once. There's a vertical line here that doesn't touch the graph at all, but that's allowed. As long as there's no vertical line that touches the graph more than once, then we have a function. So what is f of 1? I look for 1 on the graph. I look for 1 on the x-axis, and then I find where it corresponds to the graph, and we see that f of 1 corresponds to 2. So the output is 2, so f of 1 is 2. What is the domain of the function? If you notice, all the x values are used except for 1 here. We do not get a value when we try to plug in 0. There's no corresponding point on the graph that corresponds to 0. So therefore, the domain is everything except for 0. What is the range? If we notice, all y values get a value except for this guy, 1. There's no corresponding x values that give you 1. There's just a space there. So the range is all values of y except for 1. For which values of the function is the graph greater than 0? That means where are the y values positive? Positive y values are above the x-axis. So we're talking about all the y values starting from, for x values to the left of -1, and for x values after 0, we get that result. So we're talking about the interval from -infinity to -1. At -1 we get 0, or they only said positive. And then for the interval greater than 0. And so that is the domain. That is the domain and the range of this function here. I'm going to rewrite the domain using interval notation: -infinity to 0, union 0 to infinity. And the range is -infinity to 1, union 1 to infinity. That's your range values. Now let's do a quick example here to wrap up our lesson for today. So we have a graph of a function here, and we have a number of things that I'm asking us to do for this function. So all of these are questions requested. So the first part, part A, which is down here, is what is f of 0 and what is f of -6. To find f of 0, I go to 0 on the x-axis and I go up to the graph, and I see that the corresponding y value is 3. So f of 0 is just 3, because when the input is 0, the output is 3. So f of -6 then would be -3, because when the input is -6, the output is -3. What is f of 6? If I look for 6 on the x-axis, you see the corresponding y value is 0. So f of 6 is 0. And f of 11, when I look for 11, I get 1. F of 11 is 1. Is f of 3 positive or negative? So when we look for 3 on the x-axis, we realize that the corresponding y value is above the x-axis, a positive y value. So this is the 3, and you see that we don't know what the value is, but we know that it's a positive number. So f of 3 is a positive number because the corresponding y value is above the x-axis. The graph is above the x-axis. Is f of -4 positive or negative? I look for -4. That's -4 right there. And the part of the graph there is below the x-axis. So in this case, f of -4 is a negative number. Please note, the negative is not because the input is negative. It's just because it's part of the graph. I'd also like to point out that f of 6 is a negative number, right? And f of -2 is a positive number. So it's the output that determines whether the graph is a positive or negative. For what values of x is f of x equal to 0? So let's look for where f of x is equal to 0. Since f of x represents the output, the y value should be 0. So we're looking for all places where the output is 0. And we realize that those values occur at -3, +6, and at 10. And now the next question is, for what values of x is f of x greater than 0? So when does the graph give you a positive value? We see that the graph is positive starting after -3 and stopping just before 6. So we say from on the interval, we're talking about x values here, on the interval from -3 parentheses up to +6, or after 10, but up to 11, because the graph doesn't go beyond 11. So now the next question is, what is the domain of f? The domain of f are the values of x that we can plug in. The first x value we can plug in is -6, and the last we can plug in is 11, and we can use every value in between. So the domain is from -6 over to +11. And since we can plug in those numbers, we get answers for them. Those are brackets. What's the range? The range is the lowest y value I can get up to the highest y value we can get, assuming we use all the values in between. The lowest y value is -3, and the highest y value is 4. So the range is from -3 to 4. What are my x-intercepts? My x-intercepts are the places where the graph crosses the x-axis, and those are the points where the y values are 0, -3, 0, 6, 0, and 10, 0. What's the y-intercept? The y-intercept is where the graph crosses the y-axis, and that's where the x-coordinate is 0. And of course, since this is a function, there could only be one point where that is, and that's the point 0, comma 3. This is a point, by the way, not an interval. How does the line y equal to, how often does the line y equal to half intersect the graph? So the line y equal to half is a horizontal line, and it crosses, this is the point 1, 2, 3. So half crosses the graph right there, right there, and right there. That's a graph of y equals to 9. Y equals to half, sorry. Y equals to half. That graph crosses the graph of the function 1, 2, 3 times. So we have, the answer is 3 times. 3 times. And then how often does the line x equal to 5 intersect the graph? That's a vertical line. And so if we draw a vertical line, it should only cross the function no more than once. And in this case, it crosses it only once because x is in the domain. So the answer is once. And then we can go for what values of x does f of x equal to 3? So let's look for 3. We have 3 here, and if I go all the way across here, we have another value of 3 here. There are two places where f of x equal to 3. That's when x is 0 and when x is 4. So we have x equal to 0 and x equals to 4. And then for what values of x is f of x equal to -2? We see right here the y value is -2, and right here again the y value is -2. There's no other place. So those places are at x equal to -5 and at x is equal to 8. And that's it for this example. And in fact, that is it for this lesson on functions. I strongly encourage you to review the concepts, so you can review them at Khan Academy, which has great videos explaining functions in small bites, as well as great exercises, wonderful exercises for you to practice. So I strongly recommend that you go to Khan Academy and examine some of those videos and practice some of those exercises. That's all for now with this lesson. All the best.